In physics, classical mechanics and quantum mechanics are the two major subfields of mechanics. Classical mechanics is concerned with the set of physical laws describing the motion of bodies under the influence of a system of forces. The study of the motion of bodies is an ancient one, making classical mechanics one of the oldest and largest subjects in science, engineering and technology. It is also widely known as Newtonian mechanics. Classical mechanics describes the motion of macroscopic objects, from projectiles to parts of machinery, as well as astronomical objects, such as spacecraft, planets, stars, and galaxies. Besides this, many specializations within the subject deal with solids, liquids and gases and other specific subtopics. Classical mechanics also provides extremely accurate results as long as the domain of study is restricted to large objects and the speeds involved do not approach the speed of light. When the objects being dealt with become sufficiently small, it becomes necessary to introduce the other major subfield of mechanics, quantum mechanics, which reconciles the macroscopic laws of physics with the atomic nature of matter and handles the wave-particle duality of atoms and molecules, when both quantum mechanics and classical mechanics cannot apply, such as at the quantum level with high speeds. Quantum field theory becomes applicable. The term classical mechanics was coined in the early 20th century to describe the system of physics begun by Isaac Newton and many contemporary 17th century natural philosophers, building upon the earlier astronomical theories of Johannes Kepler, which in turn were based on the precise observations of Tycho Brahe and the studies of terrestrial projectile motion of Galileo. Since these aspects of physics were developed long before the emergence of quantum physics and relativity, some sources exclude Einstein's theory of relativity from this category. However, a number of modern sources do include relativistic mechanics, which in their view represents classical mechanics in its most developed and most accurate form. The initial stage in the development of classical mechanics is often referred to as Newtonian mechanics, and is associated with the physical concepts employed by and the mathematical methods invented by Newton himself, in parallel with Leibniz and others. This is further described in the following sections. Later, more abstract and general methods were developed, leading to reformulations of classical mechanics known as Lagrangian mechanics and Hamiltonian mechanics. These advances were largely made in the 18th and 19th centuries, and they extend substantially beyond Newton's work, particularly through their use of analytical mechanics. Description of the theory. The following introduces the basic concepts of classical mechanics. For simplicity, it often models real-world objects as point particles, objects with negligible size. The motion of a point particle is characterized by a small number of parameters: its position, mass, and the forces applied to it. Each of these parameters is discussed in turn. In reality, the kind of objects that classical mechanics can describe always have a non-zero size. Objects with non-zero size have more complicated behavior than hypothetical point particles, because of the additional degrees of freedom a baseball can spin while it is moving, for example. However, the results for point particles can be used to study such objects by treating them as composite objects, made up of a large number of interacting point particles. The center of mass of a composite object behaves like a point particle. Classical mechanics uses common-sense notions of how matter and forces exist and interact. It assumes that matter and energy have definite, knowable attributes such as where an object is in space and its speed. It also assumes that objects may be directly influenced only by their immediate surroundings, known as the principle of locality. In quantum mechanics, an object may have either its position or velocity undetermined. Position and its derivatives. The position of a point particle is defined with respect to an arbitrary fixed reference point, O, in space, usually accompanied by a coordinate system, with the reference point located at the origin of the coordinate system. It is defined as the vector r from O to the particle. In general, the point particle need not be stationary relative to O, so r is a function of t, the time elapsed since an arbitrary initial time. In pre-Einstein relativity, time is considered an absolute, i.e., the time interval between any given pair of events is the same for all observers. In addition to relying on absolute time, classical mechanics assumes Euclidean geometry for the structure of space. Velocity and speed. The velocity, or the rate of change of position with time, is defined as the derivative of the position with respect to time. In classical mechanics, velocities are directly additive and subtractive. For example, if one car traveling east at 60 km per hour passes another car traveling east at 50 km per hour, then from the perspective of the slower car, the faster car is traveling east at 60 minus 50 equals 10 km per hour, whereas, from the perspective of the faster car, the slower car is moving 10 km per hour to the west. Velocities are directly additive as vector quantities. They must be dealt with using vector analysis. Mathematically, if the velocity of the first object in the previous discussion is denoted by the vector u equals ud and the velocity of the second object by the vector v equals ve, where u is the speed of the first object, v is the speed of the second object, and d are unit vectors in the directions of motion of each particle respectively, then the velocity of the first object as seen by the second object is similarly, when both objects are moving in the same direction. This equation can be simplified to or, by ignoring direction, the difference can be given in terms of speed only. Acceleration. The acceleration, or rate of change of velocity, is the derivative of the velocity with respect to time. Acceleration represents the velocity's change over time, either of the velocity's magnitude or direction, or both. If only the magnitude v of the velocity decreases, this is sometimes referred to as deceleration, but generally any change in the velocity with time, including deceleration, is simply referred to as acceleration. Frames of reference. While the position, velocity and acceleration of a particle can be referred to any observer in any state of motion, classical mechanics assumes the existence of a special family of reference frames in terms of which the mechanical laws of nature take a comparatively simple form. These special reference frames are called inertial frames. An inertial frame is such that when an object without any force interactions is viewed from it, it appears either to be at rest or in a state of uniform motion in a straight line. This is the fundamental definition of an inertial frame. They are characterized by the requirement that all forces entering the observer's physical laws originate in identifiable sources. A non-inertial reference frame is one accelerating with respect to an inertial one, and in such a non-inertial frame a particle is subject to acceleration by fictitious forces that enter the equations of motion solely as a result of its accelerated motion, and do not originate in identifiable sources. These fictitious forces are in addition to the real forces recognized in an inertial frame. A key concept of inertial frames is the method for identifying them. For practical purposes, reference frames that are unaccelerated with respect to the distant stars are regarded as good approximations to inertial frames. Consider two reference frames S and S. For observers in each of the reference frames, an event has space-time coordinates of in frame S and in frame S. Assuming time is measured the same in all reference frames, and if we require x equals x when t equals 0, then the relation between the space-time coordinates of the same event observed from the reference frames S and S, which are moving at a relative velocity of u in the x direction, is x equals x minus ut, y equals y, z equals z, t equals t. This set of formulas defines a group transformation known as the Galilean transformation. This group is a limiting case of the Poincare group used in special relativity. The limiting case applies when the velocity u is very small compared to c, the speed of light. The transformations have the following consequences. V equals v minus u. equals a, F equals F. The speed of light is not a constant in classical mechanics, nor does the special position given to the speed of light in relativistic mechanics have a counterpart in classical mechanics. For some problems, it is convenient to use rotating coordinates. Thereby one can either keep a mapping to a convenient inertial frame, or introduce additionally a fictitious centrifugal force and Coriolis force. Forces, Newton's second law. Newton was the first to mathematically express the relationship between force and momentum. Some physicists interpret Newton's second law of motion as a definition of force and mass, while others consider it a fundamental postulate, a law of nature. Either interpretation has the same mathematical consequences, historically known as Newton's second law. The quantity mv is called the momentum. The net force on a particle is thus equal to the rate of change of the momentum of the particle with time. Since the definition of acceleration is r equals dv, dt, the second law can be written in the simplified and more familiar form. So long as the force acting on a particle is known, Newton's second law is sufficient to describe the motion of a particle. Once independent relations for each force acting on a particle are available, they can be substituted into Newton's second law to obtain an ordinary differential equation, which is called the equation of motion. As an example, assume that friction is the only force acting on the particle, and that it may be modeled as a function of the velocity of the particle, for example, where lambda is a positive constant. Then the equation of motion is this can be integrated to obtain where v0 is the initial velocity. This means that the velocity of this particle decays exponentially to zero as time progresses. In this case, an equivalent viewpoint is that the kinetic energy of the particle is absorbed by friction, and the particle is slowing down. This expression can be further integrated to obtain the position r of the particle as a function of time. Important forces include the gravitational force and the Lorentz force for electromagnetism. In addition, Newton's third law can sometimes be used to deduce the forces acting on a particle. If it is known that particle A exerts a force F on another particle B, it follows that B must exert an equal and opposite reaction force, minus F, on A. The strong form of Newton's third law requires that F and minus F act along the line connecting A and B, while the weak form does not. Illustrations of the weak form of Newton's third law are often found for magnetic forces. Work and energy. If a constant force F is applied to a particle that achieves a displacement delta r, the work done by the force is defined as the scalar products of the force and displacement vectors. More generally, if the force varies as a function of position as the particle moves from r1 to r2 along a path c, the work done on the particle is given by the line integral if the work done in moving the particle from r1 to r2 is the same no matter what path is taken. The force is said to be conservative. Gravity is a conservative force, as is the force due to an idealized spring, as given by Hooke's law. The force due to friction is non-conservative. The kinetic energy EK of a particle of mass m traveling at speed v is given by for extended objects composed of many particles. The kinetic energy of the composite body is the sum of the kinetic energies of the particles. The work-energy theorem states that for a particle of constant mass m, the total work W done on the particle from position r1 to r2 is equal to the change in kinetic energy EK of the particle. Conservative forces can be expressed as the gradient of a scalar function, known as the potential energy and denoted EP. If all the forces acting on a particle are conservative, and EP is the total potential energy obtained by summing the potential energies corresponding to each force, this result is known as conservation of energy and states that the total energy is constant in time. It is often useful, because many commonly encountered forces are conservative. Beyond Newton's laws, classical mechanics also includes descriptions of the complex motions of extended non-point-like objects. Euler's laws provide extensions to Newton's laws in this area. The concepts of angular momentum rely on the same calculus used to describe one-dimensional motion. The rocket equation extends the notion of rate of change of an object's momentum to include the effects of an object losing mass. There are two important alternative formulations of classical mechanics: Lagrangian mechanics and Hamiltonian mechanics. These, and other modern formulations, usually bypass the concept of force, instead referring to other physical quantities, such as energy, speed and momentum, for describing mechanical systems in generalized coordinates. The expressions given above for momentum and kinetic energy are only valid when there is no significant electromagnetic contribution. In electromagnetism, Newton's second law for current carrying wires breaks down unless one includes the electromagnetic field contribution to the momentum of the system, as expressed by the Poynting vector divided by c2, where c is the speed of light in free space. Limits of validity. Many branches of classical mechanics are simplifications or approximations of more accurate forms, two of the most accurate being general relativity and relativistic statistical mechanics. Geometric optics is an approximation to the quantum theory of light, and does not have a superior, classical, form. When both quantum mechanics and classical mechanics cannot apply, such as at the quantum level with many degrees of freedom, quantum field theory becomes applicable. QFT deals with small distances and large speeds with many degrees of freedom, as well as the possibility of any change in the number of particles throughout the interaction. To deal with large degrees of freedom at the macroscopic level, statistical mechanics becomes valid. Statistical mechanics explores the large number of particles and their interactions as a whole in everyday life. Statistical mechanics is mainly used in thermodynamics. In the case of high-velocity objects approaching the speed of light, classical mechanics is enhanced by special relativity. General relativity unifies special relativity with Newton's law of universal gravitation, allowing physicists to handle gravitation at a deeper level. The Newtonian approximation to special relativity. In special relativity, the momentum of a particle is given by where m is the particle's rest mass, v its velocity, and c is the speed of light. If v is very small compared to c, v2, c2 is approximately 0, and so thus the Newtonian equation P equals mv is an approximation of the relativistic equation for bodies moving with low speeds compared to the speed of light. For example, the relativistic cyclotron frequency of a cyclotron, gyrotron, or high-voltage magnetron is given by where Fc is the classical frequency of an electron with kinetic energy T and mass m0 circling in a magnetic field. The mass of an electron is 511 keV, so the frequency correction is 1% for a magnetic vacuum tube with a 5.11 kV direct current accelerating voltage. The classical approximation to quantum mechanics. The ray approximation of classical mechanics breaks down when the de Broglie wavelength is not much smaller than other dimensions of the system. For non-relativistic particles, this wavelength is where h is Planck's constant and p is the momentum. Again, this happens with electrons before it happens with heavier particles. For example, the electrons used by Clinton Davison and Lester Germer in 1927, accelerated by 54 volts, had a wavelength of 0.167 nanometers, which was long enough to exhibit a single diffraction side lobe when reflecting from the face of a nickel crystal with atomic spacing of 0.215 nanometers. With a larger vacuum chamber, it would seem relatively easy to increase the angular resolution from around a radian to a milliradian and see quantum diffraction from the periodic patterns of integrated circuit computer memory. More practical examples of the failure of classical mechanics on an engineering scale are conduction by quantum tunneling in tunnel diodes and very narrow transistor gates in integrated circuits. Classical mechanics is the same extreme high-frequency approximation as geometric optics. It is more often accurate because it describes particles and bodies with rest mass. These have more momentum and therefore shorter de Broglie wavelengths than massless particles, such as light, with the same kinetic energies.